Hi, my name is José Henrique Rodrigues, and I'm here to present our work at the ACC 2021, entitled Stabilization of a Nonlinear Structural Acoustic Interaction. This is a joint work with Professor Irena Lashitska from the University of Memphis. It is well known in the literature that structural acoustic models are a source of many interesting problems and therefore has attracted the attention of both mathematicians and engineers since decades ago. We would like to mention the works of Morse and Ingard from 68, Banks and Smith from 95, Faru and Wang from 99, as well as the book of Lashitska from 2002 and the references therein. Among the wide variety of applications, we would like to mention noise reduction in acoustic chambers and pressure reduction in the cockpit of a helicopter. Basic dynamics includes the interaction between acoustic waves hitting elastic walls, which will provide a feedback that is transferred to the acoustic environment. As an acoustic environment, we are going to consider a subset omega of R3, supposed to be open, bounded, and with smooth boundary gamma. The boundary gamma will consist on two connected subsets, gamma 1 and gamma naught. The portion gamma naught is what we're going to call a structural wall. And we present here two situations for this structural wall. On the left side, we present the case in which it is flat, which is going to be the case of our problem here. And on the right, the case in which it is curved. And for curved walls, we would like to mention the works of Cagnola, Lashitska, Lepietzik, and Zolazio from 2002, as well as the work of Daniels and Lepietzik from 2008, and references therein. The dynamics in the acoustic medium is given by the set of equations number 1, which consists on a wave equation with Neumann boundary conditions. On the left-hand side, we notice the presence of a locally distributed dissipation mechanism, for which the damping region is minimized by using new developments in stabilizing the wave equation with uncontrolled Neumann portion of the boundary, however, subject to geometric constraints. The dynamics in the structural wall are given by a 2D Kirchhoff-Boussinesq plate equation, subject to nonlinear effects of the structure, with a combination of blowing up forces and restorative forces, which contrast with past results where they were mostly linear plates. The full dynamics is given by the set of equations number 2, in which we notice the presence of the control operator B, which will cope with both the restoring force, known to be supercritical, and the Boussinesq source, known to cause this blowing up of solutions. Let us introduce a few notations. We are going to denote by script H the phase space, also known as finite energy space, associated with system 1, 2. It is given by the product of the corresponding phase space of the wave and plate equations. Also, we are going to denote by script E the total energy functional associated with solutions of system 1, 2. Its expression is given by equation number 3, and the positive part of this functional given by functional E correspond to the kinect plus potential energy of both wave and plate equations, whose expressions are given by equations for A and for B respectively. Therefore, the well-Posner's results read: for every initial data in the phase space H, it will correspond a unique solution which is continuous in time with values in H. Such solutions will be global in time and therefore will define a nonlinear semigroup in H, which will be continuous with respect to the weak topology. That means the continuous dependence on the initial data will occur with respect to the weak topology. These solutions will also satisfy the following energy inequality given by expression number 6. The particular case in which the boundary dissipation covers the structural wall allows us to recover the energy identity, and therefore the nonlinear semigroup will be continuous with respect to the strong topology of H. Finally, regular solutions can be obtained by considering more regular initial data. A few comments on the main issues in the proof. The restoring force is, is known to be not locally Lipschitz, and therefore the existence of solutions rely on the Galerkin method. The uniqueness of solutions require the use of logarithm control of singularities of Sobolev embeddings in dimension 2. For more details on that, we refer to the work of Lashevska and Treshov from 2006. As for continuous dependence, the obstacle here is due to the boundary dissipation, which makes the dynamics not reversible in time and therefore requires a different approach. The regularity result requires control of H3 norms of the plate solutions, which is accomplished by using the Précy-Galloway inequality and also a special basis of eigenvalues. For more details in this inequality, we refer to their article from 1980. At this point, we have established a dynamical system associated with solutions of system 1-2. Regarding the stabilization of this dynamical system, our first result follows. We assume that the control operator B has the following expression. In that case, the dynamical system will be of gradient type and Lyapunov stable provided that the dissipation mechanism covers the whole structural wall, and also the following relation between the coefficients hold. The key point in the proof is to establish the Lyapunov functional given by expression number 7, which consists on a small perturbation of the total energy functional script E. Conclusion that the system is gradient follows by applying Holmgren's theorem, and therefore the conclusion of the stabilization result will follow by exploiting the energy identity and also by showing strong convergence of solutions to the equilibria set. The case in which the boundary dissipation do not cover the structural wall is quite more complicated, and our second result gives us a partial answer to this problem. We assume that the boundary dissipation covers the non-convex portion of gamma 1, and also the, the, the relation between the coefficients given in the previous result will remain true. In that case, the solutions will converge uniformly and exponentially to zero. A few comments in this situation. Here we are dealing with a weakly continuous dynamical system, and therefore we cannot rely on the energy identity. Also, there are non-observed Neumann traces for the wave equation, which is a considerably difficult problem. And that's because the usual multipliers do not work in this scenario. Therefore, a strategic location of the acoustic boundary dissipation was needed in order to construct new multipliers that will cope with the previous issue. The main point in the proof is to establish the following inequality, for which we refer as the energy reconstruction for the system 1-2. This inequality follows by reconstructing the energy of both wave and plate problems separately. Reconstructing the energy for the wave, we arrive at the inequality number 9. We notice here the presence of a smooth vector field H, which has the property that its product with the outward unit normal vector vanishes outside the damped region gamma 1. More details on this vector field can be found in the work of Lashevska and Lebedzik from 2000. Re- the reconstruction of the energy for the plate equation is given by inequality number 10. A few comments on these inequalities. The tangential derivatives in the empty portion of the boundary are estimated using microlocal analysis. And for details on that, we recommend the work of Lasiecka and Lebiecyk from 2002. The remaining terms are computed using sharp regularity of hyperbolic traces in non-Lopatinsky cases, which is exactly the case of our problem here. So for more details on this sharp regularity, we recommend the work of ThA03 from 98. Finally, lower order terms that appear in inequality 8 are absorbed by using the damping term and also by applying a standard compactness uniqueness argument. This will lead us to the last inequality where the constant gamma is less than 1. Therefore, the uniform decay for strong solutions will follow by a standard argument and also by relying on the fact that the system is autonomous. To extend this uniform decay to weak solutions, we rely on the lower semi-continuity property of the energy functional. This concludes the proof of the second stabilization result. The references mentioned in this presentation are the following. We thank you very much for your attention.